Stop talking about how vast the universe is. We're actually trapped inside a bubble. Even more bizarrely, there might be countless other universes being born outside our bubble, with white holes creating galaxies from nothing and cosmic strings slicing through reality like blades. This isn't science fiction, it's the truth scientists are investigating right now. Follow me as we refresh our universe-level understanding every single day. Right now, hundreds of galaxy clusters are racing through space at about 3.22 million kilometers per hour, heading towards something we cannot observe. You might think the observable universe shows us everything. Imagine we are trapped inside a bubble 93 billion light-years in diameter. But this bubble is but a speck of dust compared to the world outside, out there. Universes are constantly being born like bubbles every second. Cosmic strings slice through reality like invisible blades, while white holes give birth to entire galaxies from pure energy. Hello everyone, I'm Yun Qian. That number that might short-circuit your brain is 93 billion. Scientists say this is the span of our observable universe, from one end to the other. Within this 93 billion light-year range, it's filled with stars, galaxies, and cosmic dust. You might think this is all that exists, but that is not the case. What follows is truly bizarre. The universe was born 13.8 billion years ago in the Big Bang, and the speed of light is the ultimate speed limit in our reality. Since light from those distant celestial bodies has only had 13.8 billion years to reach Earth, how can we observe objects 93 billion light-years away? This seems mathematically impossible, but the answer precisely reveals the first clue about what lies beyond our view. The entire fabric of space has been expanding. Imagine a balloon with dots drawn on its surface. When you inflate the balloon, the dots move away from each other. Even though they themselves never move on the balloon's surface, the universe operates in much the same way 13 billion years ago. When a beam of light set out from a distant galaxy, that galaxy was much closer to us. But during the billions of years, this light traveled across the cosmos to reach our telescopes. The expansion of space pushed that galaxy farther away. Today, that galaxy is 93 billion light-years from Earth. Even though its light shows us what it looked like billions of light-years away, it is this expansion that created our cosmic bubble. Inside this bubble, we can observe roughly 2 trillion galaxies. Every star you can see in the night sky, every galaxy photo taken by the Hubble telescope, every distant quasar and nebula resides within this 93 billion light-year sphere. Scientists call it the observable universe because it's all we can see. Everything else lies behind an impenetrable barrier. This barrier isn't made of matter or energy, but of time itself. Light from regions more than 93 billion light-years away simply hasn't had enough time amidst the expanding space to reach Earth. Some light is still on its way to Earth right now. The images of galaxies they carry won't be observed by humans for millions of years. The mind-boggling reality is that this 93 billion light-year bubble is just a tiny fraction of the true universe. The true universe is vastly larger than what we can see. It's like standing on a beach looking at the horizon. You can see about 32 kilometers of ocean, but there are vast continents and islands beyond the horizon. The same logic applies to cosmic space. Beyond our cosmic horizon, billions of galaxies continue their ancient dance around black holes. Star-forming regions give birth to new stars. Planets orbit distant suns, and there might even be regions of space that follow entirely different physical laws. Even more incredible, space itself is still expanding. Every second, those more distant regions are receding from us faster than the speed of light. We can never observe them. They exist in a realm forever beyond our reach. The 93 billion light-year limit isn't a wall. It's a window allowing us only a glimpse into the nearest room of the infinite cosmic mansion. And what prevents us from seeing the rest of this mansion will astound you even more. 380,000 years after the Big Bang, the universe once burst into flame. This wasn't ordinary fire. The entire universe was bathed in intense light, so strong that nothing could escape from it. Every photon was like a marble trapped in an infinite machine, bouncing endlessly between particles of matter. The universe was then as hot as incandescent white, temperatures exceeding 10,000 degrees Celsius. Much like the interior of a star, free electrons zipped around at immense speeds, constantly colliding with photons, scattering them in every direction. Light would travel just a few feet before hitting another particle. If you could miraculously survive in this cosmic furnace, you would see nothing but the immediate surroundings. The universe was completely opaque. Then everything changed in an instant as space expanded and cooled. The electrons finally slowed down enough to combine with atomic nuclei. For the first time in cosmic history, complete atoms formed without free electrons to scatter it. Light suddenly broke free, beginning to travel straight paths through the universe. This moment of cosmic liberation released a brilliant flash of light in all directions simultaneously. Scientists call this the last scattering surface. Every photon that escaped then is still traveling through the universe today, forming the cosmic microwave background radiation, and this ancient fire became the impenetrable barrier to our observation because the cosmic microwave background radiation is the first light from the early universe that could escape. We can detect this radiation coming from every direction in the sky. It's like a glowing shell encasing the space 93 billion light years away. This shell is the observational limit that no telescope can surpass. It's like trying to see through thick fog. The fog blocks your view of distant objects. The cosmic microwave background acts similarly, except it's not made of water vapor, but of ancient light radiation produced when atoms first formed. Everything that happened within the first 380,000 years after the Big Bang is forever hidden behind this wall of light and fire we cannot observe. The completely opaque early stages of the universe cannot observe the moment of the Big Bang itself, nor glimpse the cosmic events in the first few 100,000 years that shaped its form. But what truly puzzles scientists is a particular property of this ancient barrier. The cosmic microwave background radiation is almost perfectly uniform in all directions. Temperature variations across the entire sky are only fractions of a degree this uniformity seems impossible. Regions of space that never exchanged heat somehow reached exactly the same temperature. It's like turning on two faucets at opposite ends of a bathtub. The water from each faucet starts at different temperatures, yet ultimately, the water in the bathtub reaches a perfectly uniform temperature. The early universe was essentially the same. This uniformity proves that something extraordinary must have happened before the wall of light and fire formed, and this event points directly to the infinite universe we cannot access. Counting the stars in the night sky, you might reach about 9,000, the number of galaxies observable with the most powerful telescopes can reach to trillion. Each galaxy contains hundreds of billions of stars. The total number of stars in the observable universe is so vast that even if you started counting from the beginning of the universe until now, you wouldn't finish. Yet, compared to the world beyond our view, this immense collection of matter is almost insignificant. Please consider this carefully. Our observable universe extends 93 billion light-years in every direction, forming a sphere containing all detectable things. Every telescope image you've ever seen, every distant quasar, every galaxy cluster lies within this sphere. Basic geometry tells us this fact has profound implications. If you travel from Earth 93 billion light-years in any direction, you reach the edge of our observable bubble. From that new position, you could observe a brand new spherical region of space, also 93 billion light-years in diameter. Some galaxies in this new observable universe might overlap with those we see from Earth, but vast regions of it would be completely unique. If an alien astronomer existed at the edge of our observable universe, about a trillion of the galaxies they could see would be ones we on Earth could never observe. Move another 93 billion light-years further, and you'd find another 2 trillion different galaxies, and so on, extending infinitely in any direction. You'd keep discovering new collections of cosmic matter, distributed infinitely throughout space. By studying the cosmic microwave background, scientists have confirmed that on the largest scales we can measure, the geometry of space appears flat, and a flat universe that extends beyond our observable horizon has a clear implication. It is either infinite in scale or unimaginably larger than the range we can observe. If the universe is infinite, then beyond our view, there exist infinitely many galaxies. This isn't speculation or fantasy. The mathematics of cosmic inflation, combined with observations of the universe's flat geometry, make this conclusion almost certain. Beyond our cosmic horizon, there exist galaxies identical to the Milky Way, orbiting supermassive black holes. There exist planets exactly like Earth, orbiting stars similar to our Sun. The physical processes that created our solar system have repeated countless times in regions we can never observe, and most peculiar of all, because space itself is expanding, galaxies at the edge of our observable universe are receding from us at near light speed, and those just beyond the cosmic horizon are receding faster than light. This means no matter how long we wait, no matter how powerful the telescopes we build, we can never observe them. Cosmic expansion is like a one-way mirror. We can detect light from distant galaxies, but we can never send signals to them. They exist in a realm causally disconnected from our region of space. Every second, thousands of galaxies are pushed by expanding space past a point of no return, vanishing forever beyond our cosmic horizon. Yet some force from beyond the horizon is looking back, pulling our local group of galaxies into the darkness. Galaxy clusters shouldn't all be moving in the same direction. Based on everything we know about cosmic expansion, galaxy clusters should spread out uniformly in all directions. Like dots on a balloon, the recession speed of each cluster should depend only on its distance from us. The farther away, the faster. The recession in 2008, when astronomers began measuring the motions of distant galaxy clusters, they expected to see this, but the actual discovery completely overturned expectations. Hundreds of galaxy clusters were moving at speeds exceeding 3.22 million kilometers per hour towards the same region of the sky. This massive migration spans billions of light years and shows no signs of slowing down. The motion of these clusters is unaffected by cosmic expansion, as if pulled by an invisible string towards something beyond our view. Alexander Koshlinsky and his team at NASA's Goddard Space Flight Center named this phenomenon dark flow, like dark matter and dark energy. Dark flow remains an unsolved mystery. Unlike the all-directional dispersion caused by cosmic expansion, dark flow pulls matter towards a specific region in the sky between Centaurus and Vela. What's truly unsettling about dark flow is that researchers calculated that pulling galaxy clusters at such an amazing speed requires extremely strong gravity, yet there is no collection of matter in our observable universe that could generate such gravity. All the galaxy clusters, dark matter, and even supermassive black holes we can detect combined cannot produce enough gravity to drive the dark flow. The source of this cosmic pull must lie beyond the edge of the observable universe. It's like watching leaves floating down a river. You see the leaves moving, but you cannot see the waterfall around the upstream bend that creates the current. Dark flow shows us the cosmic leaves, the motion of galaxy clusters responding to a gravitational pull we cannot observe. What kind of colossal object could pull galaxy clusters across billions of light years? The most mainstream theory suggests it's related to structures formed during cosmic inflation. During the inflationary epoch, some regions of space expanded faster than light, pushing vast amounts of matter beyond our cosmic horizon. These structures might be unlike anything in our observable universe. They might contain the mass of millions of galaxy clusters, compressed into regions larger than our entire visible universe, or they could be made of exotic matter following different physical laws. Some scientists propose even stranger explanations. Dark flow could be due to gravitational leakage from a parallel universe. It could also be evidence for cosmic strings, one-dimensional curves in the fabric of space-time that could span the entire multiverse. In recent years, some studies have questioned the reality of dark flow, suggesting the observed motion might be due to measurement errors, but other research teams have continued to find evidence for this mysterious cosmic flow. The debate continues, but one thing is certain: if dark flow is real, Then beyond our view lurks something of unimaginably vast mass, and the same region of the universe might also bear the permanent scars of a collision with a neighboring cosmos. Deep in the cosmic space of the constellation Indus, there lies a bruise. This cosmic wound spans 1.8 billion light-years and appears as a cold spot. In the cosmic microwave background radiation, the matter density in this region is about 100 times lower than normal, as if something pierced reality and scooped out a huge shock of matter from the early universe. Scientists call it the CMB cold spot, and it shouldn't exist. The cosmic microwave background is the afterglow of the Big Bang, the first light released when the universe became transparent 380,000 years after its birth. This ancient light should have extremely small temperature variations across the sky, but the temperature deficit in the cold spot is so significant, it absolutely cannot be due to random chance. It's like throwing a stone into a calm pond. Ripples spread out from the impact point in perfect circles, but if you found an area in the pond where water mysteriously vanished, leaving a dry patch surrounded by normal water, that dry patch would be the equivalent of the cold spot in the CMB data. The most bizarre explanation for the cold spot involves bubble universe collisions. According to the theory of eternal inflation, our universe is a space-time bubble that formed after inflation stopped in our region, while the surrounding multiverse continues to inflate. Other bubbles form nearby, sometimes two bubbles collide before their boundaries harden into separate realities. If our universe ever collided with a neighboring bubble universe, it would leave a temperature anomaly in the CMB, like the one we observe today. The collision would compress matter in some areas and dilute it in others, leaving a permanent scar in the ancient light radiation. Computer simulations of bubble collisions show that if our universe experienced such an impact, we should observe circular patterns in the CMB. Research teams analyzed CMB data, trying to find these telltale signs. In 2010, scientists thought they had found for circular patterns matching predicted collision signatures in data from NASA's Wilkinson Microwave Anisotropy probe, but subsequent statistical analysis showed these patterns could just be random fluctuations. More detailed observations from the European Space Agency's Planck satellite failed to confirm the collision hypothesis. Other explanations for the cold spot include a cosmic void, a region of space extremely devoid of matter. Such voids can create temperature drops in the CMB through the integrated Sachs-Wolf effect. Photons lose energy, climbing out of the gravitational wells of denser regions. Some researchers suggest the cold spot could be evidence of extra dimensions, or a sign that Einstein's general relativity breaks down on cosmic scales. Others propose it might indicate flaws in our understanding of dark matter and arc energy. The cold spot remains one of the most puzzling features in the CMB map. Whether it's the result of a bubble universe collision, a product of exotic physics, or a signal of an unknown cosmic structure, its existence proves our understanding of the early universe is still incomplete, and the mystery deepens when you realize that space itself can move faster than the ultimate speed limit. Nothing can move faster than light, through the fabric of reality. Einstein's special relativity sets an absolute speed limit for all matter and energy. Objects with mass cannot reach light speed. Massless objects cannot exceed it. This cosmic speed limit governs every particle, every force, every wave in the universe, but space itself completely ignores this rule. During the inflationary period shortly after the Big Bang, space expanded exponentially in less than a second. Parts of the universe expanded by a factor of 1026 or more. This means a region smaller than a proton could inflate to the size of a basketball or larger, and this expansion occurred at speeds far exceeding the speed of light over the same distance. Imagine two ants on opposite sides of a deflated balloon. When you rapidly inflate the balloon, the ants move apart, even though they never move on the balloon's surface. Space expansion works exactly the same way. Galaxies aren't moving through space faster than light. Space itself is stretching, carrying galaxies along with it. It is this distinction that allows cosmic expansion to break the light speed barrier without violating physical laws. The implications are staggering. During inflation, regions of space once close enough to exchange light and heat were suddenly pushed beyond the distance light could cross. This also explains why the CMB is so uniform. Before inflation began, the entire observable universe was smaller than a grain of sand. Every part could interact and reach the same temperature. After inflation, these regions became causally disconnected. They could no longer exchange information or influence each other because signals would need to travel faster than light today. Driven by dark energy, cosmic expansion is accelerating. Galaxy clusters beyond a certain distance recede faster than light. We can still see some of them because their light was emitted billions of years ago when they were much closer, but the light they emit now will never reach Earth. This creates a cosmic event horizon, similar to a black hole's boundary. Information from beyond this horizon is forever lost to us, no matter how long we wait. Currently, this horizon is about 16 billion light-years away, and it expands outward every second. Inflation not only affects our ability to observe distant objects, but fundamentally shapes the structure of reality. It determines which regions of space can interact and which are forever isolated, and the inflationary process that created our cosmic bubble is still creating new bubbles in an infinite multiverse. Inflation did not stop everywhere at once. Imagine the early universe as a vast ocean of space-time, expanding exponentially in all directions. Within this cosmic ocean existed a special inflationary field that drove the expansion by stretching space faster than light for a brief period. This energy field dominated all of reality. Then, in small, randomly distributed regions of this inflating ocean, the inflationary field began to decay. When the inflationary field decayed in our region, inflation stopped. The immense energy that drove the exponential expansion transformed into matter and radiation. This transformation created a hot, dense plasma that eventually cooled to form atoms, stars, galaxies, and everything we observe today. Our observable universe was born, however, The inflationary field did not decay everywhere at once. In most of the cosmic ocean, inflation continues to this day. These regions keep expanding exponentially, stretching space, diluting matter, eventually becoming almost empty. And within this background of eternal inflation, new bubbles randomly stop inflating and convert their energy into matter. It's like water boiling in a pot. Bubbles form randomly in the liquid. Each bubble is a unique region with properties different from the surrounding liquid. Our universe is one such bubble form. In the eternally boiling cosmic pot, the mathematics of this process is fascinating. Quantum fluctuations in the inflationary field determine when and where bubbles form. These fluctuations are completely random, like radioactive decay. You can calculate the probability of a bubble forming, but you cannot predict the exact time and location of each bubble's formation. The key point is that once inflation starts, it becomes eternal. The inflationary field creates new space faster than it can decay into matter. Even though countless bubbles form every second, they occupy only an infinitesimal fraction of the total volume of the universe. Most of space remains inflating. This eternal inflation creates a multiverse of infinitely many bubble universes. Each bubble experiences its own Big Bang, evolves its own galaxies and stars, and eventually dies when its energy runs out. Meanwhile, the background space keeps creating new bubbles in a cycle repeating endlessly. Our bubble universe now spans about 93 billion light years. Other bubbles might be smaller, larger, or have completely different scales. Some bubbles might have matter densities much higher than our universe. Others might be almost empty. A few bubbles, upon formation, might have evolved completely different physical laws. The distance between bubble universes depends on the inflation rate relative to the bubble nucleation rate. Most bubbles are separated by eternally inflating space, forever unable to communicate or influence each other. But occasionally, two bubbles form close enough that their boundaries collide before the intervening space inflates too much. When this happens, the two universes collide, and the effects ripple through both realities. On the smallest scales, reality splits billions of times every second. Zoom in on any seemingly empty patch of space, down to scales smaller than the Planck length, and you'll find the smooth fabric of space-time breaks down into a churning quantum foam. Virtual particles constantly flicker in and out of existence, their lifetimes too short for any clock to measure. And this quantum foam doesn't just affect empty space, it drives the birth of entire universes. During the inflationary period after the Big Bang, quantum fluctuations in the inflationary field determine which regions would stop inflating, forming bubble universes. These fluctuations are completely random and occur everywhere. Throughout the eternally inflating multiverse, the process is as follows. The inflationary field has a specific energy value. It is this energy value that drives the exponential expansion of space. Quantum fluctuations occasionally cause the energy of the inflationary field in small patches of space to be higher or lower than the average. When the inflationary field energy drops below a certain critical threshold, inflation stops, and that region, the energy of the inflationary field transforms into ordinary matter and radiation. These quantum events happen randomly throughout space, following probability laws. In any patch of inflating space, there is a calculable probability that within a very short time interval, a fluctuation will trigger bubble formation. Multiply this probability by the infinite volume of eternally inflating space, and you get an infinite number of bubbles constantly forming. The mathematics is breathtaking. Every second, countless quantum fluctuations throughout the infinite multiverse give rise to new bubble universes. Each bubble experiences its own Big Bang, evolves its own physical laws, forms its own cosmic structures. Most bubbles are separated by continuously inflating space, never to meet. You can compare the quantum foam to cosmic seeds scattered by the wind. Most seeds fall on barren land, never growing, but occasionally a seed lands on fertile soil and grows into a full ecosystem. Bubbly universes are these cosmic ecosystems grown from quantum seeds. In the inflating multiverse, the implications of this process go far beyond just creating universes. If quantum fluctuations can give rise to infinite bubbly universes, then every possible combination of physical laws must exist somewhere in the multiverse. In some bubbles, gravity is repulsive, not attractive. In some universes, the electromagnetic force works opposite to ours. In some realities, time flows backward or in multiple directions at once. Some bubbles have physical constants, perfectly suited for life. Others become barren wastelands, where stars never form and matter cannot clump. A few bubbles might have physical properties so strange we cannot even imagine them. The anthropic principle suggests that we observe a universe suitable for life simply because we couldn't exist in those barren universes. Conscious observers like humans can only appear in the few bubbles that allow complexity to form. This means that in other bubbly universes there might be exact copies of you, living histories almost identical to yours, or differing due to different choices or historical paths. Occasionally, neighboring bubbles in the multiverse collide, triggering far-reaching cosmic consequences. There is an equation that proves infinite universes exist. This simple mathematical formula describes the probability that a patch of inflating space will form a bubbly universe within a specific time period. As time approaches infinity, this probability approaches 100%. In infinite time and space, bubble formation is an absolute certainty. The mathematics of eternal inflation is like a cosmic gamble, where the house always loses. Imagine flipping a coin forever. Each flip has a 50% chance of landing heads. Flip enough times and you're guaranteed to see heads at least once. If you have infinite coins and can flip for infinite time, you'll see heads infinitely many times. Even though the outcome of each flip is unpredictable, bubble universe formation follows the same principle. Quantum fluctuations constantly flip coins throughout the inflating multiverse. Each fluctuation has a tiny probability of triggering bubble formation. In infinite space and eternal time, bubble formation is not only inevitable, but infinite. The key is understanding exponential growth during inflation. The volume of space doubles repeatedly in extremely short time intervals, and in regions where inflation hasn't stopped. This doubling continues forever, even if the probability of bubble formation is extremely low. The exponentially growing volume of inflating space ensures the rate of bubble formation accelerates. It's like bacteria reproducing in a Petri dish. Each bacterium has a tiny probability of dividing. Within a specific time interval, initially division is slow because there are few bacteria. As the number increases, so do the chances for division. Eventually, the population explodes exponentially. Eternal inflation works similarly. Every patch of inflating space has a tiny probability of forming a bubble universe. As inflation creates more space, the number of patches that could form bubbles increases, even if the probability per patch remains constant. The total rate of bubble formation accelerates exponentially. An even more stunning mathematical conclusion comes from Andre Lin's chaotic inflation model. This model shows that when bubble universes form, their physical properties are random. The strength of gravity, the mass of the electron, the speed of light, the strength of the electromagnetic force. These fundamental constants are randomly determined as each bubble forms. This randomness ensures that across the multiverse, there is infinite diversity in physical laws. Some bubbles have gravity so weak that matter can never clump into galaxies. Some bubbles have electromagnetic forces so strong that atomic nuclei tear apart due to positive charge repulsion, and a few bubbles have physical constants perfectly balanced, allowing complexity, life, and consciousness to exist. The anthropic principle explains why, among the infinite random possibilities, we observe a universe suitable for life. Conscious observers can only arise in the few bubbles that permit their existence. Mathematical models also predict the frequency of bubble collisions. When two bubbles form close enough in space and time, their expanding boundaries eventually meet and interact. These collisions generate gravitational waves in both bubble universes. The characteristics of these waves depend on the collision angle, the relative speeds of the bubbles, and the differences in their physical properties. Most importantly, these gravitational waves leave a permanent imprint on the cosmic microwave background of each universe. How can scientists detect evidence of bubble collisions in our universe? If our bubble universe ever collided with a neighboring bubble, the gravitational waves from the impact would travel through our space at light speed, reaching the last scattering surface. These collision waves would create specific temperature anomaly patterns in the CMB, different from random fluctuations. The marks left by a collision are circular rings centered on the collision direction. Their size and intensity depend on the specific collision parameters. Matthew Johnson and his team at the Perimeter Institute for Theoretical Physics use computer simulations to precisely predict the features that different types of collisions should exhibit in the CMB map, creating detailed templates. In 2010, researchers announced they had found for possible collision signatures in data from NASA's Wilkinson Microwave Anisotropy Probe. Each signature was a set of concentric rings with temperature variations matching theoretical predictions. This discovery suggested our universe might have collided with for different neighboring bubbles. However, subsequent analysis revealed flaws in this interpretation. More detailed CMB maps from the European Space Agency's Planck satellite showed that these seemingly collision-related patterns were likely statistical flukes. Random temperature fluctuations can sometimes coincidentally form ring-like patterns. Scientists are still searching for collision signatures using more refined methods. New analysis techniques can distinguish real collision signatures from random patterns by examining multiple statistical properties simultaneously. Finding definitive evidence of a bubble collision would revolutionize our understanding of cosmic reality. This discovery would prove our universe is just part of a vast multiverse and that other realities exist beyond our cosmic horizon. Collision evidence would also provide our first observational window into studying the physics of the multiverse, understanding how bubble universes form and interact. Meanwhile, the search for collision signatures has revealed an even stranger possibility: the existence of bubble universes whose fundamental laws of nature are completely different from ours. In some bubble universes, electrons have masses comparable to protons. Gravity is repulsive. Each bubble universe, upon formation, randomly acquires its own set of physical laws: the strength of gravity, masses of fundamental particles, speed of light, strength of electromagnetic force. These parameters are randomly chosen from the vast array of possibilities during bubble nucleation. Most parameter combinations result in barren universes where nothing interesting can happen. Imagine a universe with gravity 10 times stronger than ours. Cosmic gas would form stars more easily, but these stars would burn through their nuclear fuel in just millions of years. Stellar explosions would be so powerful that entire galaxies would be sterilized by radiation. Strong gravity would crush all planetary surfaces, preventing complex chemistry. Conversely, if a bubble's gravity were 10,000 times weaker than ours, matter would never clump into stars. Galaxies would exist as thin, cold gas drifting through space. No nuclear fusion, no formation of heavy elements, no planets, and certainly no possibility for life. Changes in the electromagnetic force would have equally dramatic effects. If slightly stronger atomic nuclei would tear apart due to charge repulsion. If slightly weaker, electrons would spiral into atomic nuclei, eliminating chemistry entirely. Some bubble universes might evolve entirely different particle physics. In these realities, the fundamental building blocks of matter follow alien rules. Particles that attract in our universe might repel there. Forces that weaken with distance here might strengthen with distance there. The strangest possibility is the existence of universes with different numbers of spatial dimensions. We live in a 3D space plus 1D time reality. Other bubbles might evolve with 4, 5, 10, or even hundreds of spatial dimensions. Motion in higher dimensional space would be a completely alien experience. Objects could appear from directions that don't exist from our 3D perspective. A 4D sphere passing through our 3D space would mysteriously appear and disappear. String theory suggests that bubble universes with compactified extra dimensions might be quite common. These extra dimensions are curled up so tightly they appear point-like from our 3D view, but they affect the properties of fundamental forces and particles. Some theoretical physicists propose that advanced civilizations in other bubbly universes might have mastered technology to manipulate their local physical laws. By understanding the relationship between space-time geometry and physical laws, these civilizations might alter fundamental constants within limited regions. Such physics manipulation technology might seem like magic to us. They might create regions where gravity flows backward, where time passes at different rates, or where matter transforms according to different rules. The anthropic principle suggests that most bubble universes are barren. Only a tiny fraction of bubbles can form conditions suitable for complexity and consciousness. This means intelligent life in the infinite multiverse is extremely rare and precious, but within our bubbly universe, perhaps not only are there exotic physical phenomena beyond the distant horizon, within the observable universe, there might also exist objects that warp reality. In some corner of the cosmos, black holes have an evil twin. They don't destroy, but create. Black holes swallow everything that comes near, while white holes do the exact opposite. These theoretical objects violently expel matter and energy with astonishing force. Nothing can approach their surface. They are like cosmic geysers, spewing enough matter to form galaxies into space. The other side of the universe holds not just more space, but infinite forms of existence itself. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries, and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.